Hi everyone, and welcome to week 11, multivariate regression. I hope everyone had a reasonably good spring break, if you can call it that. I think the older you get, the less of a spring break it really is. But hopefully you did get a little bit of a chance to review anything if you were having trouble, or catch up on any papers for either this class or another class. But yes, again, if you are having questions or troubles, feel free to reach out to me. So this week's lecture is really sort of a natural extension from our week on bivariate regression. So I don't think that you should have too much trouble with it. So let's get into it. The logic is largely the same. So with multivariate regression, if you'll recall from bivariate regression, it was between one continuous dependent variable and one independent variable, right? Because this was bivariate. In the case of multivariate regression, though, we're talking about, again, it's still one continuous dependent variable, and a continuous variable is something like income, weight, age, and then with multivariate, though, you can have multiple independent variables. You'll have multiple independent variables. Usually it will include like your one that is primarily of theoretical interest, right? What your theory speaks to, but you'll also be controlling for other things that you think might affect your dependent variable. The equation, though, is largely the same, and every time I bring up the equation, people are frightened. Don't be frightened. Don't be frightened. So what we can see here, y is our dependent variable. It equals alpha, which is our intercept, beta 1. So in our original from a few weeks ago equation, we only had this component, and this component. We're adding on more variables, right? So each of these, this beta 1 x1, beta 2 x2, and beta 3 x3 are variables, right? So beta 1 is the slope, right? Or coefficient for our variable x1, plus beta 2, which is the slope for our variable x2, plus beta 3, which is our coefficient for our variable x3. And then finally, this little u here, that is our error term. So that's just everything that we don't end up explaining in our model, right? So before, we just had alpha plus beta 1 x1 plus the error term, and we didn't have this beta 2 x2 and this beta 3 x3. It was bivariate. So all we've added are these new terms for any additional variables that we might have, okay? But the equation is largely the same, with alpha being our intercept, this little u being our error, the betas being slopes or coefficients for each of our variables, and then the x's being each of our variables that we're going to be including in the model. So let me give you an example real quick. So here's an example. Say that I am interested in body mass index, right? And that is a measure that is your weight divided by your height times a constant. So in this case, if your BMI, body mass index, is under about 18, that's considered underweight. If it is between about 18 and 25, that's considered normal. If you start getting above 30, though, that's considered obese, right? And say I'm interested in explaining how one gets a certain body mass, right? We might survey 1,000 people, And I'm specifically interested in whether someone's BMI is affected by access to grocery stores. This is my variable of theoretical interest, right? I'm interested in how access to grocery stores affects body mass index, with the idea being that if you have access to healthful foods at grocery stores as opposed to say at a convenience store, right, where there's a lot of like frozen and processed food, if I have access to grocery stores, I might expect this body mass index, my dependent variable, to be lower. Whereas people who have not very much access to grocery stores, right, say they're only near sort of fast food or convenience food stores, I might expect them to have higher body mass index scores. But is access to grocery stores the only thing that affects body mass index? No, right? There are lots of other things that you can think of that will affect your body mass index. So as a consequence, we need to control for that, right? And the reason that multivariate regression is so good is because it allows you to control for this sort of multifaceted world that we live in, right? There's not only one thing that affects a dependent variable. There are lots of different things. And so it also will let me control for other factors like caloric intake, activity levels, right? With the idea being that people who consume more calories likely weigh more. People who are more active likely weigh less, right? They have lower BMIs. Age, the notion being that those who are older tend to have slightly more body fat than those who are younger. Gender, women tend to have slightly higher fat levels or BMIs relative to men. Ethnicity, certain groups have higher or lower BMIs compared to non-Hispanic whites. For instance, Asians tend to have lower BMIs relative to non-Hispanic whites. And muscle mass, right? So some people that are like athletes will actually have higher BMIs, right? They'll have more muscle, which in turn is heavier than fat, and so they'll have higher BMIs because of that. So these were the things that I would control for if I really wanted to determine whether access to grocery stores does have an effect on body mass index. In order to say whether access to grocery stores has an effect on body mass index, I need to control for the other things that will affect body mass index, right? I can't just run a bivariate test between body mass index and access to grocery stores and say, yep, there's an association, which means there's a relationship. I have to rule out a lot of other causal mechanisms and things that might affect one's body mass index. And that's sort of the beauty of multivariate regression, is that it lets you control for all of these. Okay, so just a brief note about how it works with multivariate regression. So as noted a couple of weeks ago, bivariate regression was about the line of best fit, right? And it was about minimizing these errors between our observations and the line of best fit. So the line of best fit tries to ensure that these errors between the line of best fit and our observations are minimized. Now, this was between just two variables, right? The independent variable is along our x-axis and the dependent variable is along our y-axis. What happens when we include more variables? Well, it becomes sort of a three-dimensional figure, right? It becomes a three-dimensional figure. With multivariate regression, at least in this case, this is between three variables. Specifically, it's this is about trees. This is tree data. And it says the independent variables are girth of the tree and height of the tree and how much volume in like cubic wood you get out of it. And so what we can see here, right, girth is like how far around, like how round the tree is, and height is how tall it is. And so it has fit rather than it being a line, it has fit a plane, right? It's fit a plane through this to minimize the errors between this plane of best fit, right? So this is our plane here, this grid, and it's trying to minimize the distance between our observations in this three-dimensional space and the plane, right? The logic is really similar to this. It's trying to minimize the distance between our observation and our line of best fit. In this case, we're just trying to minimize the distance between our observation and the plane of best fit. It's very similar logic here. But ultimately, it's trying to minimize those errors to best fit this data. But let's jump into the lab so that we can start interpreting some results, right, with some coefficients and R-squareds and stuff. But yes, this is mostly a logical extension of the bivariate regression.